AP Chemistry, we're now on to Lesson 6 in the Acid Bases unit. So in the last lesson, Lesson 5, we looked at how acids react with different combinations of water and bases. In this lesson, we're going to turn it around and look at how bases react in different combinations of water and acids. So here's an overview of what we're going to talk about in this lesson. First, we're going to talk about a strong base in water. Well, we've talked about that already in earlier lessons. There's a complete dissociation of a hydroxide ion, OH-, from either an alkali or alkaline earth metal. So the one we use the most frequently in class is sodium hydroxide, NaOH, and that breaks apart from the hydroxide, the sodium and the hydroxide. It could be potassium hydroxide, it could be calcium hydroxide. There's about 8 of them. So that's the first one. The second one is a weak base in water. So what a weak base does is it accepts some, usually a very small number of protons from a water molecule to produce a hydroxide ion. In other words, it breaks a water molecule in two. And the weak base takes the proton on, and then it leaves behind in the solution the hydroxide, the OH-, which is simply a water molecule minus a proton. Now we're going to mix excess strong base and strong acid. We're going to put strong base and strong acid together. Excess means that we're going to have the strong acid is going to run out first. It's going to be consumed first. That would make it the limiting reactant. So the excess reactant will be the strong base. So in this case, the strong base accepts all of the H+ protons from the strong acid to produce a neutralization reaction, H2O. So you have an OH that's been produced by the strong base, and it takes the hydronium ion, the H+, from the strong acid, then you have H2O, and that's a neutral substance. After the strong acid is completely consumed, then the strong base is going to produce hydroxide ions. It's going to continue to break apart into, for example, sodium and hydroxide ions to produce OH- hydroxide ions in the solution. Next, we have excess strong base with a weak acid in water. So the strong base will accept all of the H+ protons from the weak acid to produce water molecules, just like the strong acid. The excess strong base dissociates to leave hydroxide ions in solution. And finally, we mentioned that we don't talk about weak base and weak acid reactions, and nor will you be tested on them on the advanced placement exam. Okay, so first we're going to talk about the strong base in water, and that's going to completely dissociate if we're talking about sodium hydroxide as our strong base, the sodium is going to break off from the hydroxide, and you're going to end up with as many hydroxide ions in the water as you started with sodium hydroxide. So if you start with 1 molar NaOH, you'll end up with 1 molar OH-. So here's an illustration of that. In the acid-base section before, we dealt with acids reacting in water. Now we're going to deal with bases. So in pure water, a strong base such as sodium hydroxide, NaOH, will 100% dissociate into the Na+ and the OH- ions. So sodium hydroxide is a strong base because it contains a hydroxide ion. So we put it into the water. And in water, a strong base will completely dissociate into the metal cation and the hydroxide ion. The creation of a hydroxide ion, OH-, is what defines a base and can react with an acid later on. The metal cation, in this case the sodium, does not react any further. Now we're going to look at a weak base in water, and that accepts some, usually a very small number of protons from the water molecule producing OH-. So whereas the strong base that gave off an OH carried its own hydroxide, that would be an Arrhenius base. Here you have a Bronsted-Lowry base which accepts a proton. So we're going to use ammonia as our example here. So when a weak base such as ammonia, NH3, is placed in water, it will occasionally pull a proton, an H plus, away from the water molecule. So there, that proton on that particular water molecule is going to jump over to the ammonia atom. So the result is the ammonium ion NH4 plus and a hydroxide ion OH minus. In this situation, water acts as an acid by donating a proton to ammonia. So the ammonium ion NH4 plus is the conjugate acid of ammonia. In other words, they differ by one proton. Take an ammonia molecule, NH3, add a proton to it, you have NH4 plus. The hydroxide ion is produced when the water molecule loses a proton. Now we'll look at an excess strong base and strong acid. So you have strong acid, strong base in solution together, but there's more of the strong base than the strong acid. So the strong acid is going to be the limiting reactant. It's going to run out first, and you're going to have some strong base left over. So what happens? The strong base accepts all of the protons from the strong acid, and when you put a proton together with a hydroxide ion, an OH minus, it produces a neutralization. It produces a water molecule. That's a neutral substance. It's neither acid nor base. After the strong acid is consumed, the strong base produces hydroxide ions in solution. That means the solution starts to become more basic. So at first, the strong acid and strong base neutralize each other to form water molecules. Once you run out of the strong acid, then the strong base is just going to dissociate just like it did up in the very first reaction. The Na is going to break off from the OH in a case of sodium hydroxide, and you're going to produce hydroxide ions, and that's what defines a solution as a base solution. A pH above 7 is the presence of hydroxide ions. So here we have an illustration of that. So you can see that you have two sodium hydroxide molecules over on the right and one hydrochloric strong acid molecule on the left. So there's more strong base in this example than strong acid. So first, the NaOH will be placed into the water. By the way, in these sequences, you don't have to do the reaction in exactly the order I'm showing. I'm just doing it one step at a time to make it more understandable rather than putting everything in the water at the same time. So first, the NaOH will be placed in the water, and the Na plus and the OH minus will dissociate. So go to your solubility rules. Sodium, Na, dissociates. It breaks apart from anything that it's with, including hydroxide ions. So the OH ions will accept protons, H plus, from the HCl 100% of the time. Okay, so now you have a neutralized acid molecule. That hydrochloric acid is no longer an acid. It's just a Cl minus ion, and the chloride ion is neither acid or base. It does not change the pH of the solution. Similarly, you turned a hydroxide ion, OH, into a water molecule, which is also neutral, so it doesn't affect the pH of the solution. Since you ran out of acid molecules, you cannot neutralize that second hydroxide ion, and therefore it's going to contribute to the solution being more basic. Not as much as it was before when it had two hydroxides, but it is still a basic solution with a hydroxide ion there. So this creates a neutral H2O molecule, leaving just one OH minus in the solution. The solution was basic before the HCl entered the solution. After the HCl reaction, the solution is still basic, but less so. In other words, it only has one OH minus ion instead of two. Okay, now we'll look at excess strong base with weak acid in water. So the strong base accepts all of the H plus protons from the weak acid to produce water molecules. Then the excess strong base, after the acid has run out, dissociates to leave hydroxide ions in solution. In other words, the weak acid with the strong base with weak acid behaves exactly the same way as the strong base with strong acid. The strong base will totally take on the protons from the weak acid. The weak acid will give up every weak acid molecule will give up a proton, 100%, to a hydroxide ion. And then after the weak acid has been consumed, been used up, then the rest of the strong base, say the NaOH, will break into Na and OH and leave hydroxide ions in the solution. So here we have one weak acid molecule on the left, and again, two strong base molecules over on the right. So the strong base outnumbers the strong acid. So first, the NaOH will be placed in the water. Again, the order in which you do this is not important. The sodium and hydroxide ions will dissociate, so we don't care about the sodium ions on the bottom. They're spectators. But we have two hydroxides. That's made the solution basic. It's now a base solution with a pH above 7. We care only about the hydroxide OH ions. Next, the hydrofluoric acid is placed in the solution. Again, the order doesn't matter. Now, so what's going to happen now is we know that hydrofluoric acid only partially dissociates in water. It's a weak acid. But when there's hydroxide ions around, it always dissociates to donate a proton to the hydroxide ions. So the OH minus ions will accept protons H plus from hydrofluoric acid or any weak acid 100% of the time. This means that hydrofluoric acid, a weak acid, behaves like HCl, a strong acid, as long as it's in the presence of hydroxide ions. They will both totally donate protons to a hydroxide. This creates a neutral H2O molecule, leaving just one OH minus hydroxide ion in solution. The solution was basic before the hydrofluoric acid entered the solution. After the hydrofluoric acid reaction, the solution is still basic, but it's less so. Instead of having two hydroxide ions, you only have one. So it's still a base solution, but less so than it was before. Here we will place several weak acid HF molecules in solution with a strong base, sodium hydroxide. So place the NaOH in water. Again, the order of HF and NaOH doesn't matter. The NaOH will dissociate into Na and OH ions. It is only the OH minus ions that are important. So there it goes. The HF weak acid is next placed in the solution. Again, just to make the example more understandable, we do it one at a time, one step at a time. Okay, so how many of the HF hydrofluoric acid will dissociate to the hydroxide ions? Well, we really answered that question already. Hydroxide OH has such a strong pull on protons that it will cause 100% of weak acid molecules to dissociate. So in other words, in the presence of hydroxide, a weak acid acts the way a strong acid acts. It will totally dissociate. This means that every weak acid molecule that enters the water will give a proton to a hydroxide ion. In the presence of hydroxide ions, OH minus, a weak acid will 100% dissociate to hydroxide, but not 100% to water. Again, it's a weak acid. It doesn't totally dissociate to water. But to hydroxide, a weak acid will 100% dissociate. This means that a weak acid will neutralize, turn to water molecules 100% of the strong base OH minus ions in solution. And finally, weak base, weak acid, as we said in the previous lesson, we don't discuss that. It's complicated and you're not going to be tested on it. So here's a summary of everything we've talked about. In water only, strong acids totally dissociate to H2O to produce hydronium ions, H3O+. Weak acids partially dissociate to H2O to produce hydronium ions. Strong bases totally dissociate a hydroxide, OH-, from an alkali or alkaline earth metal. Again, sodium hydroxide, calcium hydroxide, they will totally break apart 100%. That's the definition of an Arrhenius base. The base has the hydroxide on the molecule already, and it releases it in a water solution. Weak bases partially accept a proton from an H2O molecule to produce OH minus ions. So it breaks a water molecule in two. The proton goes over to the weak base, say ammonia, and the OH minus remains behind in solution, making it a basic solution. So that's the definition of a Bronsted-Lowry base, that the base is a proton acceptor. It took a proton away from water. Now, strong and weak acid in water with a strong base. Strong or weak acid in water with a strong base will totally dissociate a proton to the hydroxide until the hydroxide is consumed. Then the acid behaves as in water up above. So the strong acid will behave as it says up above at the top, and the weak acid as it says up above as well. A strong weak base in water with a strong acid. The strong or weak base in water with a strong acid will totally accept a proton from a strong acid until the acid is consumed. Then the base will behave as in water only. So whether it's a strong base or a weak base, it's totally going to take on a proton from a strong acid. Then once the strong acid runs out, then the strong base will and weak base will behave as described up above in just water. And weak acid base, we don't talk about those. Okay, so that takes care of this lesson. It's a short one. This is due on Wednesday, but please try to get it done a little bit sooner than that. We're going to be moving into a pretty heavy topic next week, and I want you up on acid bases before we do that. Okay, so we'll see you on the next lesson.